All right, welcome back, Algebros. This is our exponential functions lecture as we go through here. So these go along with your Unit 6 packet. We can go ahead and next here. Why are we learning exponential functions? Well, one reason is because our finances, right? Here's a chart of if you start saving money in your 20s versus starting when you're my age or starting when you're 40. Right? We have these exponential curves that we deal with, right? These are exponential equation. Here is your compound interest formula. I know we dealt a little bit with that earlier in the year. We're gonna come back to that, but right now we're gonna focus on the very basics. So go ahead and go to the next one. So this is in your packet to use the properties of exponents to be able to simplify and solve and sketch graphs of exponential equations. So the very basics, what is the exponential parent function? Well, in your notes, right, I want you to put y equals a times b to the x. Now notice where the x is. The x is in the exponent. And I have a b, a number being raised to the x. If this b is greater than 1, well, this function is an exponential growth and is increasing. All right. If your b is less than 1, it is exponential decay. And you have a decreasing function. So the very basics in the SAT, a lot of tests love to ask you to make an exponential equation, and it's really easy. Our A is just our starting point, right? That's the quantity that we start with. That's often where your y-intercept is going to be as well. Our b is our growth or decay factor. Growth or decay, and I call it a factor because we need to manipulate it. If I wanted to know, or if I knew how something doubled over a period of x, I could make my b 2, right? If I wanted to know, oh, it increases by 10%, for every period x, well, my b would be 1.1. I would add 1 to it while I'm dealing with increases in percents. Now, what if it's decay? Well, if I know the half-life of something, my b would be 1/2, right? If it's dividing by half every so often, or decreasing by half, I would have a 1/2 of b, and that would be an exponential decay. If it's decreasing by 10%, right, I just do 1 minus 0.1 or 0.10, right, 10%, and my b would be 0.9 to the x. So I can find my b because I know, if I know what is it's increasing or decreasing, or if I have a half-life or a doubling time, and I can always find my a, which is the starting point. So I should be able to write exponential equations from word problems. All right, go ahead and go next. So a couple misconceptions to go over. Now, quick. These are not polynomial functions. Exponential functions has an exponent, a variable in the exponent, not the base. So here's our polynomial function. We have x cubed. All right, we've dealt with a lot of polynomial functions. We can have big numbers in the exponents. That is different from a number to the x, right? This is exponential. This is cubic, right? Or it could be a part of a polynomial function. So an exponential has a variable in the exponent, not the base. Here's a vocab word that is on your packet. An asymptote is a number that a line approaches. Shouldn't be lines. A line approaches but never reaches. And so this is in your packet. Make sure to fill in that definition. Exponentials do have asymptotes. They're usually at 0 if we haven't moved our exponential function up or down, and we'll explain why that is. And again, we have to know the general form, right, of an exponential. Y equals A times B to the X with the X in the exponent. So go ahead and go to the next. All right, so your first graph on that packet, it is Y or G of X to the 2X. On your packet, I believe it says Y. All right, so what we're gonna do, we're gonna click through here and we're gonna fill out a table and we're gonna graph this point. So go ahead and click. So at 2, right? Well, if I plug in a 2, I get 4. At 1, I get 2. At 0, anything to the 0 power is 1. At -1, I get 1/2. At -2, right? Well, what is that? Well, that's 1 over 2 squared, right? So you get 1/4. So I'm getting really, really close to 0 here, right? So this line down here, as I'm getting smaller and smaller fractions, but because these fractions are just getting, the denominator is just growing, right? It's getting close to 0. That is an asymptote at Y equals 0, all right? Well, what is my y-intercept here? Well, I know my y-intercept, right? It's 0, 1, 0, 1. All right. What is my end behaviors? Well, as x goes to infinity, y is also going to go to infinity. As x goes to negative infinity, right? This way, well, what does y go to? Well, that is getting closer and closer to 0. Remember, I have that asymptote. So my domain and range, well, my x values, it's hitting all the x values, right? So it's all real numbers. That's not there. All real numbers. My range, right? My range, we go from 0 all the way to infinity. So y is greater than 0. All right. So this is the first one in your packet, right? Fill it up. You have number 3 and number 5 to do for homework. All right, continue on. So let's review the properties of exponents. I've shown this multiple times already this year. Keep going. There's 8 of these properties. We use them to solve equations, and we're going to talk about one more special property today, and it's going to give you the key to do a lot of your Get More Math problems, which, by the way, you have 84 Get More Math points. Make sure you get on that. So look at these, see which ones you know, pick out 2 or 3 of them. If you know how to do them, good. If you went 3 for 3, that means you probably know it. If you went 1 for 3, you need to study these. Go ahead and move on. So okay, yeah, keep going. All right, so 2 times 2, this is one of our exponent properties, right? We can add the exponents, right? Makes it really easy. So keep going. Here we add the exponents, we get to a -4, right? Well, now I know my reciprocal rule. I can do 1 over 2 to the 4th. I get 1/16. All right, same thing here. Power rule, 3 times 2, 2 to the 6, which is 64, right? I can use all these properties of exponents. Go ahead and click through. Hopefully I can do it with fractions as well, right? Distribute, flip, right? Cube. Over here, we subtract on our quotient rule, 3 to the -2, that's 1 over 3 squared, 1/9. Down here, we're multiplying fractions, right? I could undistribute 2 times 8 to the 1/2, which is 16 to the 1/2, which is just the square root of 16, which equals 4. All right, so hopefully we know that. All right, stop here. So now we get to the exponential equations, all right? So I have 5 to the x, and I have equals 125. Well, the new thing for today is known as the change of base theorem. If I can get this to have the same base, then I can drop it. So how can I write 125 in terms of 5 to a number? Well, I know I could write it as 5 cubed, because that's the same as 125. So since I can do that, I can now drop the base and I get x equals 3. All right, so I'm going to let this play out. All it is if I can get the same bases, I can drop it. So let's do another one. All right, we're going to solve 7 to the x minus 1 equals 7 to the negative 1/2. Well, here the bases are already the same. So click ahead. Now I can just drop them. I can get rid of that 7. And I can set x minus 1 equal to negative 1/2. I can add 1 to that side. And I can solve negative 1/2 plus 1 does give you 1/2. Right? Makes it pretty easy. Let's click next. So here's another one. I have 8 to the x equals 2. Well, how could I express 8 to the x in the same way as I can express 2 to the 1? So what could I write 8 as? Well, I know 2 cubed is 8, right? 2 times 2 is 4 times 2 is 8. So 2 cubed to the x equals 2 to the first. Well, what do I do here? Well, that's an exponent rule. That's my power rule, so I multiply. So this is 2 to the 3x equals 2 to the 1. Change of base. 1 equals 3x. Divide by 3. I don't know why I switched sides there. All right, I'm going to switch back. X equals 1/3. Right? Soon as I get the same base, I can eliminate it, set it equal. All right, let's go play it out. So, pretty simple. Now over here, I have 8 to the x equals 4. Well, how can I get both of them common? Well, if I'm going to get them in common, let's put them in terms of 2. So 4 could be 2 squared. And again, 8 could be 2 cubed. And again, it's to the power of x. So I need to multiply it. So this is 2 to the 3x equals 2 squared. Now I can drop it. 3x equals 2. Divide by 3. I get x equals 2/3. All right, hopefully that's clicked through over there. Good. All right, let's do a few more examples. Now I have 1/3 to the x equals 27. Well, how can I rewrite this? Well, if I know my exponent rules, I can rewrite 1/3 as 3 to the negative 1, right? 3 to the negative 1 would mean it would be 1 over 3 to the 1. So now I have 3 to the negative 1 to the x equals, well, 27, I know I can rewrite it as 3 cubed, right? So again, power rule. So this is 3 to the negative x equals 3 cubed. Now they're the same, so I can drop it. Negative x equals 3. Multiply by negative 1 on each side, and I get x equals a negative 3. All right, let's click through it. Oh, look at that. All right, another one over here, last one. So I normally, hopefully in your class, I fooled you on this one, right? Because this is not an exponential equation. It doesn't have a x in the exponent. It's x to the 1/3. Now, I don't need to do change of base. I can solve this using my rational logic. Well, what is 1/3? How would I get rid of it? Well, it's the same as the cubed root. So how do I get rid of it? Well, I cube both sides, right? 1/3 times 3, so that's going to be x to the 1, or x to the 1 power equals 27 cubed. So what is 27 cubed? Well, it's 19,683. So make sure we understand what we're dealing with. Go ahead and click next. All right, so here, again, it's not considered, but I do need to know how to get rid of this one, right? 3/4, I would take 8 to the 4/3 power. So go ahead, multiply by the reciprocal. This is something I've seen students struggle with. Make sure you have that tool in your tool belt where you can multiply by the reciprocal to get rid of that one as well. All right, so again, you could write it that way. It simplifies in your calculator. Yes, you do get 16 here. Let's go ahead to the next one. All right, general forms. All right, just remember exponential equations, right? For all values greater than 0, right, we have a number being raised to an exponent, right? If all it is a machine. A function is just a machine that takes inputs and gives output. Go ahead and go to the next slide. All right, so big thing I need you to remember. Make sure we have our change of base and make sure we can tell the difference between decay and growth, right? If it is greater than 1, right, this is going to be growth. It's a big difference between a function going like this and one that's coming like this. If your x, if your b value is less than 1, it will be decay. The function never crosses the x-axis, right? Because we get really close. We have that asymptote at y equals 0. The x-axis is a horizontal asymptote. All right. Go ahead and go to the next slide now. So this should be decay. So smaller base, right, means the graph rises more gradually. Larger base means more quickly. That's our starting value. That's our A. Exponential functions will not have negative bases. So we won't ever have a negative starting value. All right, the number E. You're going to see this pop up in a lot of exponential equations. All it is a number around 2.71. All right. You may have heard of this as Euler's method. Maybe if you watched the movie with the NASA people, the black engineers that got us the computers that got us to space. Y'all know what I'm talking about? Hidden Figures. There we go. Hidden Figures. They do Euler's method in Hidden Figures. Anyway, it uses this number. Go ahead and continue. Don't get confused. The way we find Euler's number, right, is we take the limit of 1 plus x to the 1 over x. It equals 2.71. You don't need to know that, but you do need to know that 2.71 is around what E is. And it's a mathematical constant that we use and you can calculate. Go to the next one. Euler, like I said, he was a Swiss mathematician. All right, Hidden Figures, use that trick. If you want to, impress your parents, tell them you know how Hidden Figures, how the math works. So go ahead and go to the next. So basic exponential function, you can have e to the x. We modeled that with population increases. Remember, my x is still in my exponent, so this is an exponential function. It doesn't change anything. It's just the constant that's greater than 1. So of course, this is exponential growth. All right, continue. All right, so also, right, very common. We can have exponential decay. This is a half-life equation. So I just want to show this example. Go ahead and click continue. Half-lives, right, we will look like this. You'll see that problem on like uranium active decay. A lot of radioactive material has half-lives, so we use that a lot. It's tested a lot. Go ahead and continue. So this is the last slide, right? You have growth and decay, right? Decay, you're going to look at carbon-14 dating, half-lives. We actually use these in real science. Growth, rumors have exponential growth. Human population, bacteria, technology, nuclear chain reactions, and compound interest are all real-world examples of where we use exponential growth. So exponentials are really important. I hope you all pay attention to this unit and master these exponents. Thank you.